Okay, now let's start our discussion of time dependent perturbation theory. In time dependent perturbation theory, we are going to uh, deal with Hamiltonians that are time dependent using perturbation analysis. Okay, so in the perturbation analysis, what we have done is, suppose you need to solve for a particular Hamiltonian H cap. So you have to have a situation which is kind of close to the actual problem or the actual situation for which you know the exact solution, so that you will take it as h naught, and whatever comes as extra you will take it as an h prime, and this is the way you will divide the Hamiltonian, and then later you will do the analysis and find out uh, uh, the corrections in energy as well as states. Okay, in this situation we have to do exactly the same way, but the uh, perturbation component is having a time dependence, and that will make the Hamiltonian also time dependent. So that is a kind of Hamiltonian that we have to solve. For example, let us take the case of a hydrogen atom incident with the beam of radiation having energy h mu. Okay, so in this case, you know the Hamiltonian of hydrogen atom. So I'll take the Hamiltonian of hydrogen atom as h cap or hydrogen. Okay. So before the incident radiation have any effect on hydrogen atom, I know the Hamiltonian of hydrogen atom, that is having a potential energy as well as kinetic energy. This is something that is known for us. Okay, so during a period of time, a radiation is getting incident on this hydrogen atom, so that will modify the energy of hydrogen atom, and there is certainly some sort of a change, and that will modify the Hamiltonian into a new Hamiltonian, that is your h cap, which is actually a combination of this hydrogen atom Hamiltonian before this incident plus whatever energy is there due to the interaction, and that I write it as V of t. So this is your perturbation in this case, that depends upon the time during which the whole incident happened. Okay, so now I can write this V of t as V of t during a time between, let's say, t naught to t1, but before t less than t naught or after t1, t greater than t1, this is 0. Okay, so only during this time t0 to t1, this incident this potential are really acting on that, so during that period of time you have a Hamiltonian. So after the time interval, the Hamiltonian will be coming back to this particular form again. Later h cap will become something, it's a combination of kinetic energy and potential energy. Okay, one important difference that you can notice here in the case of Hamiltonian that have time dependence is that uh, you don't have to worry about the you don't really have uh, no energy ion values. You don't have energy ion values in this case. So this is because our wave function in the complete form is actually having the spatial as well as time components, And when we are deriving the time independent Schrodinger equation or the eigenvalue equation, we have made the factorization of this wave function into spatial as well as time parts. However, when the Hamiltonian is having it, whenever the Hamiltonian is having a time dependence, this kind of a factorization is not possible, and so we really don't have any energy and values. So that is one important difference in comparison with the time independent case.
So if you look at the example of hydrogen atom here, the Hamiltonian before the interaction is time independent, and for this Hamiltonian you can write the energy eigenvalue equation as we discussed before. So here you have energy eigenvalue for the hydrogen atom, and after the interaction has gone, again the Hamiltonian is time independent, and you can write the energy uh, eigenvalue corresponding to different states. And whatever energy and value you are going to get here need not be the same as the initial state, because there can be some sort of transition because of the time dependent Hamiltonian over here. There will be transition between the state, and the energy and values in that case cannot be the same. So this is not required to be the same. The state will get, there will be transition between the states, and the state will get modified due to the time dependent Hamiltonian. Okay, so if you look at our example of hydrogen atom, the Hamiltonian before the interaction is time independent, and in this case you can find out the energy and values by using your energy and value equation, time independent form. And after the interaction, again the Hamiltonian is time independent. You can find out the energy and values in this case also. So during the interaction, the whole states are having uh, an interaction term which depends upon time. So that is keep on changing the states, and you really don't have the uh, idea of energy and values here. Okay, finally after time t1, this is getting frozen into a particular value, and later onwards there is no change for the Hamiltonian, or the states are going to be fixed with whatever number you have. So you can calculate the energy and value corresponding to that state. So I'll take psi I as my initial state, and this state is getting modified due to the interaction. This is getting modified, and after time t, this is, it became psi f, the final wave function. Okay, so the idea that I have to do here is actually I need to find out the final wave function. So I know the initial wave function, I know the initial states, and I just want to find out what is going to be the final state. Okay, so we can solve this kind of a problem conveniently in interaction picture. So I'll go to interaction picture. So this is something that we have discussed in detail in QM1. So I'm not going to the details of the picture. So this is actually applicable for interaction even something like that we have discussed already in the example. Uh, so it's applicable for Hamiltonian that are time dependent of the form h naught plus h prime that is having a time dependence, or you can also take it as some v cap of d. This is as the interaction is having a potential associated with that. Mostly this is case. Okay, so um, okay, so let us call the initial wave function here. Just to briefly mention what happens here. Uh, let me take my initial wave function. Wave function at a time t naught is my initial wave function, say of t naught. and after some time this will change into psi of t. So this evolution of the wave function can be accounted by an operator called time evolution operator u. So that u, whenever it is acting on the wave function, initial wave function, it will produce you the final wave function. So uh, that is called the time evolution operator, and it's represented by u cap, from where the time is taking to the time it is reaching. Okay, so u cap of psi of t naught will produce you the final wave function. So you know the complete form of u cap. This is something we have done already. I'm not going into that. Or okay, this is a way we will actually convert between time dependent wave function to time independent wave function. So suppose in the Schrodinger equation you are using time dependent wave function, say of t, you can convert that into the time independent form. See this quantity over here, this is time independent because this is the initial wave function, and the initial wave function is going to be whatever time, irrespective of the time, that is going to be the same all the time, right? Okay, so this quantity, if you are able to calculate, okay, how do we do that? Psi of t naught is u dagger of psi of t, right? Okay, so this we call actually Heisenberg wave function in the Heisenberg picture. And interaction picture is actually a combination of both the Schrodinger and Heisenberg picture. And in interaction picture, we define the wave function. Okay, this is to just illustrate this point that we can write an operator of this manner. So in interaction picture, I'm not doing that. I'm going to define psi of t interaction as an operator e raised to I by h cross h naught t, h naught t. So this is actually slightly different from your u operator. U operator will be of this form. Sorry, u dagger operator will be of this form, but it will be having the complete Hamiltonian. But in this case, we only have the h naught, that is a time independent part. Okay, so this operator with the actual wave function. Uh, so any the wave function at a time t, so that is being multiplied with this quantity. I defined it as the interaction wave function. Okay, so that is a definition that I give, and such kind of a picture will give you the Schrodinger equation of this form: h cross dou psi of t by dou t is equal to vi into psi of t, and this is interaction picture. This is also, and vi is actually not our v of t, and both of them are connected by using e raised to I h naught t by h cross, or v of t e raised to minus I h naught t by h cross. So that is the way v of I and v of t are connected. So this is our Schrodinger equation in interaction picture. Okay, now uh, we have to do a little modification. Our aim is actually to find the wave function at a later time psi of t in interaction picture here. So that connect from a time t naught. So t naught to some t, we have an evolution, and our aim, we know this quantity. Initially, we know the Hamiltonian. So our aim is to find out what happened for the system at a time t. Okay, so the wave function, according to my definition, psi of t naught is psi of t psi of t interaction I defined it as e raised to I h naught t divided by h cross into psi of t, and the psi of t I can write. I know the psi of t is a time dependent wave function, and the time dependence on that wave function is coming from an operator, time evolution operator, that changes it from t naught to t. So I'm just writing it as I h naught t by h cross u cap from an initial time t naught to a time t. Okay, of psi of t naught, psi of t naught. That is the initial wave function. Okay. Okay, so this is actually not in interaction picture. This is actually in the wave function. You can it is the actual wave function at the initial time. You can say that. Okay, so here I want to convert this back to the interaction picture because we are interested in the interaction uh, wave function and the evolution of that interaction wave function. So we know this is at time t, and this also I want to put it in interaction picture, so that will become like here is to I h naught t by h cross u of t t naught and psi of t naught connect with psi of t naught at interaction picture. How do that connect? Just a reverse of this is psi of t from this. Okay, so this is like minus of that quantity, that will become a raised to minus I h naught t divided by h cross into your psi of t naught interaction. Okay, so we got uh, so here what happened is psi of t at a time t will obtain from psi of t naught in interaction picture when you apply this whole operator. So it's not just u operator, an operator with this kind of a structure. Okay, so this operator I will call it as a u in interaction picture, and this is being called u t t naught in interaction picture. Okay, so psi of ti is nothing but ui of t t naught psi t naught in interaction picture. So that is the wave function, and I just substitute that value in our Schrodinger equation. Here I will substitute the value. So what will happen? Okay, IH cross dou by dou t. Time dependence is there associated with your wave function. Okay, this will be coming along with the your psi of ti. You substitute this, and the time dependence is carried with this operator. So it is dou by dou t of u cap of t t naught. What is IH cross psi of t naught is equal to vi let it be vi, and the wave function is going to be u interaction. This is also u interaction of t t naught into psi of t naught in interaction. Okay, so here the psi of t naught in interaction, this quantity really does not do anything. We can get rid of that. This is the new Schrodinger equation is of this form: dou by dou t of u I t t naught is equal to vi u I of t naught. So this is our finally Schrodinger equation that we need to solve. Okay, so how do we solve this expression from here?